This is the second episode in a series covering the design and construction of a clock for my relay computer. In the last episode, I explained why my computer needs a clock and exactly what it is a computer clock does anyway. This time I'll start looking through how I can approach building one and the design choices I might consider. Here's where we got to last time. I'm looking to create a consistent square wave at a rate of 6 cycles per second, 6 Hz, on a 50% duty ratio. That breaks down to roughly 167 milliseconds per cycle with a pulse width of 83 milliseconds. Our target amplitude is 12 volts, which is the standard voltage for pretty much everything in the computer. What I didn't cover last time is why I'm targeting a rate of 6 Hz. Well, it's kind of in the Goldilocks zone, not too fast, not too slow. But truer to say is that it's around the same rate as the relay computers I took inspiration from, and if it's good enough for them, then it's good enough for me. So when thinking about how best to implement the clock, a good place to start is with the simplest thing that might work. For me, I'm thinking maybe starting with something like a basic motor. If you could find a way of switching on the power when, say, the spindle is at the 3 o'clock position, and then power off at the 9 o'clock position, then you'd have power on half the time and off half the time. Effectively, you're producing the square wave. Easiest way I can think of doing this is with the latching relay. This can be set on with one microswitch and then reset with another. To make this work, a cam is attached to the motor spindle and rotates. Hitting the first microswitch, setting our relay and sending the clock output high. It then carries on rotating. Hitting the second microswitch, resetting our relay and sending the clock output low. This is nice and simple, and you can control the speed of the motor to change the clock frequency. It's quite an attractive option too, as it's very mechanical, which fits nicely with the computer's overall design. In terms of other pros and cons, as mentioned, you can vary the clock speed by altering the motor voltage, within limits of course, and you can easily stop and start it. That said though, when I stop the clock, I want it to pause in the off position, not in the on position, and this is so I can manually drive the clock via the front panel switches. I guess I could set it up so that when the motor power is switched off via the stop switch, then some basic logic gates will keep the motor power going until it reaches the off position. Effectively, the logic will say if you're not powered by the switch, then take your power from the relay, which will ensure the cam stops shortly after the second micro switch. Being open and honest, this is not wholly my own idea, and I've seen this used on a relay computer that calculates square roots. I'm not sure if it operates exactly as I've described here, but it looks very similar to what I have in mind. Okay, that's idea one. The second idea for this is not an original one either. I've mentioned a few times that my computer forms part of a lineage back through Phil Riles and team's RC3, which you can visit at the San Antonio Museum of Science and Technology, by the way, right through to Dr. Harry Porter's computer. Both of these use a relay ring counter as a basis for their clocks. And that makes sense, a relay computer running on a clock which is itself made of relays. From a high-level viewpoint, you effectively set up a ring of relays which turn on and off in sequence. Goes something like this. Such that only 2 neighbouring relays are on at any one time, and that's because each relay is providing power to the relay ahead of it and cutting off power to the relay behind it. Looking at the outputs of each relay, you get these pulse trains. To obtain a clock signal, we apply some binary logic that states the clock is high when A and D are high, or when B and C are high. The magic behind the magic here is the use of an RC network at each relay coil to control the length of time each relay is held on after its power supply has been cut. Pros cons wise, this design is very authentic in my view, but operates at a fixed clock speed. Once designed and set, then that's it. It'll also be a challenge to get the resistors and capacitors set at an appropriate value to get the exact clock timing I'm after. It might be slightly off 6 Hz, but not so much it'd be a problem. Otherwise though, it's all good, and as with the RC3 computer, I'll be able to stop and start the clock with some appropriately designed circuitry, and, more importantly, the computer itself will be able to stop the clock when instructed to by the use of a halt instruction. And if nothing else, I'm drawn to this design in terms of the amount of relay noise it will make. Moving on from the more mechanical clock designs, something that's quite ubiquitous when it comes to timing in the electronics world is the 555 chip. This little wonder can be used for a variety of timing, pulse generation and oscillator applications, and is, as the saying goes, cheap as chips. It's been around for ages too. No, I really do mean ages. These things first rolled off the production line in 1971, and any electronics hobbyist is bound to have come across one in their travels. In this case, I'll be operating it as in a stable multivibrator, which sounds exciting, but just means that it's not stable in either the on or the off state, and left to its own devices happily flips between those states in a steady fashion, which is exactly what we're looking for. Because we're now getting into integrated circuits, I'll need to make sure that the 555 chip can drive the output relay. This chip is actually tough as old boots and can happily drive up to 200 milliamps, so should be okay with my relays, but I'll probably pass it through a transistor just to be on the safe side. Setting up our output signal is just a case of choosing the right values for the capacitors and resistors, but if we want to make the frequency variable, then that gets more interesting, especially when trying to keep the 50% duty cycle. Either way, it's a topic well outside the scope of this video. Rest assured, it is possible though. If you're interested in more detail on the 555 timer, there's a great article here at Electronics Tutorials, which explains more. Well worth a read in my opinion. Rightio, so this would give us what we need and could be made adjustable, but what I'd quite like to do is have discrete clock speeds that I can pick from. Which brings me to my fourth design option, and it's quite an obvious one when you think of the visual metaphor I've been banding around this series so far. It's my humble IKEA clock, which does a pretty good job of maintaining a 1 Hz signal. These clocks, like most cheap ones, have a quartz crystal at their heart, which vibrates at 32.768 kHz. You may have spotted that's a power of 2, and so if you keep dividing the signal down by 2, you eventually get to 1 Hz. What do I mean by divide by 2? Well, you can run the clock signal through something called a flip-flop, which will change state on every rising pulse coming in. This has the effect that it changes state half as often as the input, effectively giving you an output signal which is half the frequency. In other words, it's divided the frequency by 2. You can chain these flip-flops together to keep dividing by 2 until you get the frequency you want. This is perfect for what I need here. When flip-flops are chained together like this, they effectively form a binary ripple counter, because each output is representing the values 1, 2, 4, 8 and so on. Each rising clock signal on the input will increment the overall binary value present by 1. Likewise, if you look at this diagram another way, the 1 slot is changing half as fast as the clock, and the 2 slot is changing a quarter. It's dividing the clock by 2 in stages. As you might imagine, there's chips available that hold all this functionality in a single package, and all we'd do is use these to take us right down to the slowest frequency we might want to use, which, let's say, could be half a hertz. Given these ripple counters expose all the intermediate frequencies, we can also take an 8-channel selector chip, so we can pick one of 8 inputs given a 3-bit selector value. This is a nice tidy solution and gives me a range of speeds, all with excellent accuracy. Not that my computer particularly needs it, but there we go. And being honest again, this design is neither unique nor new to the computer. This is exactly how the little temporary timing board works I've had in my computer for some time. I adjust the clock frequency via the dip switches, which then picks off the appropriate frequency from the ripple counters. So, 4 different options, but what to go for? To help eliminate some of the options, let's first put down some requirements. Chiefly, it needs to produce a well-formed square wave at 6 Hz. Bonus points if it can output a range of frequencies, and I also need to manually start and stop the clock when required. If I do stop the clock, the signal being output should rest in the off 0 volt position so that I can manually operate the clock line. This will be used in debugging scenarios or if I just want to manually clock an instruction through. There should be a halt instruction that allows the program to stop the clock and pause execution. Lastly, I'd like to get a whiff of authenticity into the clock and keep the electromechanical theme going. So let's check the scores. The motor clock supports everything I want and I consider it authentic. Full marks. The relay ring clock is definitely authentic but operates on a fixed frequency, so only scores 5. The 555 chip supports everything but breaks from the electromechanical theme, and the crystal clock also supports everything but likewise breaks from the theme, so scores 5. Okay, I mean that didn't clear the ground as much as I hoped. There's no clear winner and they're all fairly decent candidates. Alright, decision time. I can drop the 555 timer, as the crystal can do the same job and is arguably simpler and more accurate, and I prefer the discrete frequencies choices over a variable range. The motor option I really like, but if I'm going to have to pick between that and the relay option clearly has to win, given my computer is then being true to its parent and grandparent computers. Down to 2. And that's difficult now because I kind of want them both. I want the authenticity of the relay clock, but I also really like the discrete frequency choice of the crystal clock. I'll tell you what, I'll be greedy and have both. It should be no problem to make a design that puts both on the same card, and then I can have a small switch to choose which clock to run from. Excellent, okay, that's a good place to leave it for this video, I think. In the next video I'll take a closer look at the details of making a relay ring clock, and I can come back to the crystal design later on.